does not translate from here to there. So maybe.
Hello. Good evening to all of you, and very warm welcome to this session. This session will have 3 talks. The first talk is by Professor Rahul Srivastava. He is from the Department of Physics, IISER Bhopal, and he'll be talking about current neutrino physics, a theoretical status. Please welcome.
Give me a heads up 10 minutes before my time ends.
Sure.
I'm going to give you the printout of 10 minutes. I hope I am audible. Backside, am I audible? Okay, perfect. So before I start, I will pitch. Okay. So before I start, I will like to thank the organizers for giving me opportunity to talk here, and also for a very well organized conference. This is a massive conference, and it was a massive undertaking, and I can only imagine all the effort the organizers have to put. So big thanks to them. Now coming to the topic of the talk, I will be talking about the current theoretical status of neutrino physics, and because the topic is current, so I will mostly focus on developments which have happened in last 10 or 15 years. Okay, so this is a brief line of my talk. So because my talk is the first one in the neutrino session, I will briefly mention the experimental status. Of course, there is an experimental talk following me, where you will learn more details about what all experiments are going on and what is the status. But I will briefly mention it just for sake of completeness. Then I will come to what are the open questions remaining in neutrino physics, and as you see, there are a lot. Then I will talk about what are the proposed solutions to these open questions, and as I said, I will focus more on the recent progress. I will also talk about how neutrinos relate to other issues with standard model physics and the open questions in other sectors, and is there a connection between neutrinos and other issues in standard model physics. And then I will talk about little bit about phenomenological implications. So what we know, first thing we know is neutrinos exist. They are not a hypothetical particle, we have detected them, and we know how they are related to other fundamental particles within standard model. Okay, we also know that there are 3 flavors of active light neutrinos. There might be more flavors, but we know that only 3 flavors of light active neutrinos are there. By active, I mean the ones which take part in electroweak interaction. Okay. Now we also have for almost 25 years we have seen neutrino oscillations, which is basically neutrinos change flavor even in vacuum, and this neutrino oscillation phenomena has been used to obtain crucial information about leptonic mixing matrix. So here is a chi-square fitting of the various oscillation parameters. This I have taken from the Valencia group. There are 2 other groups, the Bari group and the Newfit group, and their results pretty much agree with each other with small deviations from each other. So as you see the neutrino parameters are very well measured, some of them. In particular, I will like to point out the two which are ill measured, which is the atmospheric mixing angle theta 23. There is a octant ambiguity in the atmospheric mixing angle which we have not yet resolved. And then you can see that the CP violation, the situation is not at all clear. Few years back, it seemed like the CP violation is for both normal, so blue line is normal and the pink is inverted. So few years back, it seemed like CP violation for both scenarios was converging towards maximal CP violation, but now as you see that for normal hierarchy, the situation has changed. So it's still a evolving measurement. Apart from, and here is the global fit parameter. So as you can see, we have measured almost all of them apart from the CP phase. And first thing is there are two mass square differences. First one, which is the mass square difference between the second and the first eigenstate. We also know the sign, so we know that the second eigenstate of neutrinos is more massive than the first one. Whereas for the 3-1 case, we do not know the sign. So that's where the origin of the two orderings, mass orderings is there. There is a possibility that the third eigenstate is lighter than the first one, which is called the inverted ordering, or the normal ordering where the first one is the lightest and third one is the heaviest. And as I said, because of this ambiguity, the mixing parameters also for both orderings are listed, and theta 23 because delta M21 is measured with the sign, so theta 12 there is no ambiguity. Now apart from neutrino oscillation parameters, we have other experiments which are trying to measure other properties of neutrinos. So for example, Catherine experiment is now running, and it has not been able to measure mass of the neutrinos, but it has put bounds. Notice that Catherine does not directly measure the mass eigenstates, but rather it measures a combination of the mass eigenstates and angles, which is called m beta, and the latest bound from Catherine is 0.8 electron volt. We also have bound from cosmology, which from the Planck's last data set, full data set, we get a bound of sum of neutrino masses to be 0.12 electron volt. Now here I should also point out that this limit depends on the priors used, and you can relax this limit. I have taken the one which is the most stringent. Okay. Then the nature of neutrinos is not known. I will talk about that in more details. So basically, neutrinoless double beta decay is the way, the holy grail signature which will uniquely determine whether neutrinos are Majorana particle or not. If you see the neutrinoless double beta decay signature, then thanks to the Schechter-Wale black box theorem, we know for sure that neutrinos are Majorana particles. So far we have not seen any signature, and Kamlan-Gent bound I have put it here, which has put quite stringent bound on another combination of mass eigenstates and mixing angles and phases called m beta beta. And this difference here that you see, the two numbers quoted, they depend on the estimations of the nuclear matrix elements. Okay, so different estimations give you different numbers. So this is very quickly the current experimental status. So now the question is what we don't know. So the point is that we don't know many of the things. Okay, it has been more than 80 years since the neutrinos were first proposed, and still we know very little about them. So the very nature of neutrinos, whether they are Dirac particles or Majorana particles, is still not known. The Dirac and Majorana nomenclature is used for fermions, and by Dirac particles we mean that the fermion, the particle and the antiparticle are distinguished by some symmetry. Okay, Majorana particles are their own antiparticles, and there are only very special certain symmetries which allow for Majorana mass term, as we will see. Neutrino mass generation mechanism is also not known. In standard model, as you know, neutrinos are massless. So how to generate neutrino is not known. Not known means we do not know experimentally. There are a lot of proposals for them. For example, there are these famous seesaw mechanisms, I'm pretty sure all of you have heard the name. And what I have shown here is the diagrammatic way of representing the three type of Majorana seesaw mechanisms, type 1, type 2, type 3. Just for the students how to read these kind of diagrams, these are mass diagrams, okay. So each diagram will have two external lines which are fermionic lines, okay. And then you can have bunch of scalar lines. There will always be two external fermionic lines. You can have bunch of scalar lines. Here these are the lowest order ones, so there are only two scalar lines. And these lines basically signify that the mass of the neutrino is going to be proportional to the coupling times the web of this scalar. Okay, so there are two insertions like that here, which means whatever the neutrino mass will be directly proportional to the two Yukawas times the web. For Majorana case, as you see, both are same. It is so it will be the electroweak web square proportion. And you can see for all of them, the external lines are same. And there is a reason for that. We will come to that. Apart from these seesaw mechanisms, which are what are called tree level mechanisms, there are also loop level mechanisms. And I have just put one of the loop mechanisms. There are other known ones. So this is called photogenic model, and again we will revisit it. And again you can see the external lines are exactly same, and we will come to it why that's the case. Okay. Now is recently in last few years, people are also talking about hybrid mass mechanism, where the neutrino masses are not just generated by either tree or loop, but rather a combination of tree and loop. Okay, so this is an example of a hybrid mass mechanism where the solar scale, if you recount, there were two mass scales measured from the neutrino oscillation parameters. The solar scale is coming from the loop, and the atmospheric scale is coming from the tree level. Apart from mass generation mechanisms, we do not know the scale of the mass generation mechanism. What I mean by that if you look at any of these diagrams, there are some new particles that have been added, which are not present in the stand model. What are their masses, etc., we do not know. So again, for the mass scale, there are two types of models in existence in literature. One are called the high scale models, and by high scale models we mean that the masses of these particles for order 1 Yukawas is going to be very large. So for example, take example of type 1 seesaw. If I take the Yukawa couplings, the couplings here to be order 1, then the masses of these intermediate new particles that I have added will be roughly of the order of 10 to the power 14, 15 GeV. Okay, so way out of reach of any conceivable experiment. So that's what we mean by high scale, and all of these seesaw mechanisms that you see, they are all examples of high scale. The intermediate particle, for example, here the NR, here the delta, or here the sigma, they are all going to be very massive for order 1 Yukawa. Apart from that, there are some low scale models also, and the unique feature of low scale models is that the intermediate particles can be in the GeV-TeV range. Why that happens? So for example, this inverse seesaw is the most famous example of such kind of models. There is a parameter here which is given by this coupling lambda times the web of this field, which typically in literature is known as mu parameter. And this mu parameter, in the limit of mu parameter going to 0, there is an enhanced symmetry in the Lagrangian. Hence, by naturalness condition, this mu parameter can be naturally small. And if this is naturally small, this in turn allows for order 1 Yukawas, the masses of these intermediate particles to be in the GeV-TeV range, satisfying the bounds for light neutrino masses. So these are called low scale. There are other examples also. So that's the scale. Then, as I said, we have not able to measure yet the absolute masses of the neutrinos. We have only upper bound from Catherine and cosmology. Then neutrino mixing and oscillation patterns, right? So as I showed that the oscillation patterns are now measured, okay, but there are some ambiguities. For example, theta 2, 3, the octane problem is still there, and delta Cp we do not know. Again, there are a lot of proposals in theory which predict certain patterns for theta 23 and delta Cp. More often than not, both together. Okay. Unfortunately, because of lack of time, I will not discuss these kind of models here, because they themselves are a talk in their own. So apart from that, this ordering problem, whether third eigenstate is heavier, which is the normal ordering, or the third one is the lightest, we do not know. Okay, again, there are more theoretical proposals where this ordering can be fixed, but again, I will not go into details because of lack of time. Okay. Finally, there is also the problem of how many numbers of generations of neutrinos are there. As I said, we know for sure that there are only 3 active light neutrinos, that is neutrinos which take part in electroweak interaction and are light. Okay, but there can be other neutrinos which are called sterile neutrinos, which do not take part in electroweak interaction directly. Okay, and they can also be light, and these kind of neutrinos are called sterile neutrinos, and we do not really know how many sterile neutrinos or if any sterile neutrinos are there. And there is a recent interest in sterile neutrinos because of certain anomalies that we are seeing in certain experiments, and again, that's a topic for experimental talks, and in fact, in parallel session, several people have talked about these anomalies. Okay. Finally, how neutrinos connect to other open problems, for example, baryon-antibaryon asymmetry or dark matter physics. Some of these I will talk about. And as I said, I will only be able to cover certain aspects of certain theoretical aspects of neutrino physics, partially because of lack of time. Also, some of the topics are beyond my expertise. Some of the topics are covered in parallel session, and some of them are very well known, for example, seesaw mechanism. So, I mean, the topics omitted are not unimportant or anything. It's just that I have to pick and choose. So, let's go to certain theoretical proposals, and let's start with the question whether neutrinos are Dirac or Majorana particles. Okay. So, as I said, we have no idea of so far if neutrinos are Dirac or Majorana particles. Okay. And the problem is the V minus A nature of standard model. Okay. Because of the V minus A nature of standard model, all observables which are sensitive to the nature of neutrinos are suppressed by powers of mass of neutrino by the energy scale of the experiment. Okay. So that makes it very hard to pin down these. Has it stopped working? Working. Okay. So it's very hard to pin down such kind of effects because they are timed. Okay. So you need very precise experiments. So as I said, neutrinoless double beta decay is the clear, unambiguous signature thanks to the Schechter-Wallee black box theorem. Apart from that, you can also tell distinguish between the Dirac and Majorana neutrinos. For example, if you see LHC signatures of lepton number violation, depending on what kind of signatures you see, you can make certain cases. Also, there is this possibility that Catrine measures mass of neutrinos, and we have not seen neutrinoless double beta decay. The combination of two will imply Dirac nature of neutrinos. There are loopholes there in the argument, but just as a rule. The reason is that the sensitivity of Catrine experiment is not that much, and if neutrinos are Majorana, within the sensitivity range of Catrine, we have not seen any neutrinoless double beta decay signature already. So if now Catrine comes and measures the mass of neutrino, that will be a strong indication that maybe neutrinos are not Majorana. Okay. So this is the experimental status. What about theory? So up to few years back, like roughly 5, 6, 7 years back, there was an overwhelming consensus among people working in neutrino physics theory that although we have not seen the signature for Majorana neutrinos, neutrinos must be Majorana. And there are reasons for that. I will not go into details, but we will see why that kind of impression was there. But now this kind of thing, there is a re-thought process going on in the community, whether we should be so sure that neutrinos are indeed Majorana. And the reason is that one has to, the way to look for Dirac or Majorana nature theoretically is to try to see the lepton number breaking pattern of the neutrinos. So as you know, lepton number is an accidentally conserved symmetry in a standard model. Now, if lepton number remains a conserved symmetry, then neutrinos will be Majorana because, will be Dirac because Majorana mass terms are forbidden by the lepton number symmetry. However, this is an accidental symmetry of the standard model. It's not on the same footing as the gauge symmetries, for example, color symmetry. It's not on the same footing. So, there is a possibility that actually lepton number is violated. It's just that we have not been able to experimentally reach the scale of lepton number violation. So in such case, one has to look at lepton number breaking pattern more carefully. Now, what is really a lepton number? It's a U1 symmetry. In simple terms, you can think of it as a symmetry of a circle on a complex number line, complex plane. Now, this lepton number admits subgroups, which are what are called abelian cyclic groups of element M. What are these things? They are symmetries between special points. So, for example, most of you must have heard about parity symmetry. Mathematically, it's what is called Z2 symmetry, Z equal to M equal to 2, okay, the smallest subgroup of U1 symmetry, and Z2 symmetry is nothing but symmetry of two special points on this circle. Then after Z2, there is Z3 symmetry, M equal to 3, and that is a special symmetry between 3 points, okay, and these Zn symmetries can be very conveniently represented by roots of unity. So, for example, Z2 is represented by the square root of unity. It has two eigenvalues, -1, +1, sorry, +1, -1. Z3 will be cube root of unity. Z4 will be fourth root of unity. It will have 4 charges, etc. and etc. So, you can so you can parameterize them by roots of unity, okay, and then the fields will carry charges which will be powers of this omega, where omega to power m will be always 1, okay. So, now one has to look at lepton number breaking pattern more carefully to decide whether neutrinos are Dirac or Majorana particles, and let us start with breaking of lepton number, because number is, if it is conserved, then neutrinos are for sure Dirac. So, when it is broken, one has to look what subgroup is left unbroken. Oh, already. So, what subgroup is left unbroken? So, if it is a odd subgroup, then neutrinos are always Dirac. Odd subgroups are Z3, Z5, Z7, etc., etc. Because you can show that Majorana mass terms are forbidden. If it is a even subgroup, Z2, Z4, etc., etc., then you have to look in more details, because neutrinos can be either Dirac or Majorana. Then how will you decide what is the case? You have to look at the representations of the lepton doublet of which neutrinos are part under this even symmetry. So, if they transform as exactly omega to n, remember omega to power 2n will be 1, 2nth root of unity. So, if they transform exactly like this, then they will be Majorana. Any other transformation, you can show that the Majorana mass term is forbidden by this symmetry. So, if you look really from symmetry point of view, then Dirac neutrinos are more natural than Majorana neutrinos. Okay. So, now the next question is why people thought that Majorana neutrinos are more natural or neutrinos will appear more naturally, and the answer is this operator. Way back in 79, Weinberg wrote down this operator, and this you can recognize from the previous figure. This is the operator which has the external legs of the previous figure. So, this is an effective operator, this is a non-remergible operator. You add this operator, you can add this operator to a standard model using only standard model fields. Okay. Now, the unique thing about this operator is that this guy breaks lepton number always to Z2, and Z2 being the smallest subgroup has this unique property that it has only two representations, +1 and -1, and both of them satisfy this condition for Majorana. So if you make this operator, if you UV complete this operator, you will always end up with Majorana. And all the models that I showed you are nothing but UV completion of this very operator. So whenever you will UV complete this operator, you will always end up with Majorana neutrinos, whether it is tree level or loop level. And that's what people were doing. People were writing various UV completions of the Weinberg operator, and they were always ending up with Majorana neutrinos, which gave a kind of a false impression that Majorana neutrinos are more natural. But now, as I said, there is a revisit going on, and the reason is that one has to look at the number more carefully. In fact, actually, there are two symmetries which are accidental, baryon number and lepton number, and this combination B minus L can be made anomaly free if we add right-handed neutrinos to standard model. And the vector solution, where you add right-handed neutrinos, give them same charges as the standard model neutrinos, was known from 70s, and if you use this solution, you will always end up with Weinberg operator and breaking to Z2. But if you use the other solution which is now known, then what you will do, you will forbid this operator, which is the problematic operator. This is the tree level coupling between neutrinos, right and left, and you can write down now Weinberg-like operators for Dirac neutrinos. Now you notice I have to add a new scalar field to make this operator invariant under B minus L symmetry, and this is new scalar field carries 3 units of B minus L charge, which means it is going to break B minus L symmetry to Z3M, okay? Which means that, for example, if M is 1, then this is Z3 symmetry, and you remember Z3 symmetry always lead to Dirac neutrinos. So all UV completions of this operator will give you Dirac neutrinos. And now people have written down all kind of UV completions of this kind of operators, and you get lot of models for Dirac neutrinos, in fact, as many as you can write. Okay, so that's one thing, and since I am running out of time, let me skip all these models and just directly go to some connections between neutrinos and other problems in physics. So the first one is dark matter. You know that dark matter exists, and in standard model there is no good answer for dark matter. Dark matter has to satisfy certain properties. It has to have some symmetry which stabilizes the dark matter. It doesn't let it decay. It should not be electromagnetically charged or should have very small electromagnetic charge, should satisfy relic density, etc., etc. Right? Now, traditionally we treat neutrinos and dark matter as two separate things to be addressed. But the question is, are they intimately related with each other? And the answer is, was found like 15, 16 years back. One of the connections was found by Ernest Mah, which is now called scotogenic model. So you add these two fields and UV complete the Weinberg operator. So this is a model for Majorana neutrinos. Okay, and you can shrink this circle and you can see this is nothing but Weinberg operator, right? Now the idea of Ernest Mah was to add a dark symmetry, a dark parity symmetry, give all the external fields +1 charge and internal fields -1 charge, and then the field which is lighter of the two -1 charges fields will be stabilized by this dark parity symmetry. Okay, it cannot decay, and it will become a good candidate for dark matter. People have done all the phenomenology of this thing. There is another connection which was found years back, and let me just explain it quickly with example of a example. So this is connection between Dirac neutrinos and dark matter, and let me show you by example. So here is a model for Dirac neutrinos. You can see this operator is not Weinberg operator, but rather one for Dirac neutrinos. And what you see on the left are the B minus L charges of the called, again the fields inside the loop are all beyond standard model fields. And when you break this B minus L symmetry, you see that these internal fields have odd powers of this, here it is breaking to Z6, so 6th root of unity, odd powers of 6th root of unity. And the external fields have even powers, and hence the lightest field inside will be a completely stable particle. This mechanism only works for Dirac neutrinos. So there are two connections. One is the scotogenic model, which is a special type of mass mechanism. This is a model which is, this is a mechanism which is generalized, skip the generality part, but it only works for Dirac neutrinos. Okay, and since I am, how much time I have? Okay, since I am running out of time, let me go to other things where neutrinos connect. So for example, Higgs vacuum stability. We have measured, we have seen a 25 GeV scalar some 10 years back, and if it is a standard model Higgs, then you can actually go ahead and compute various properties of standard model, because standard model is now complete. There are no free parameters left. Okay, and you can in particular calculate the Higgs vacuum stability, and you will find that this is the range. The Higgs vacuum stability is particularly sensitive to top mass. Okay, so this plot is little bit old. Now the circles have shrunk, and we know that in the standard model the Higgs is metastable. Okay, and the largest uncertainty or the largest impact on Higgs vacuum stability is because of the top Yukawa, which is the largest coupling in standard model. Now, if you have neutrino mass mechanism, then top Yukawa need not be the largest coupling in the theory. Okay, in fact, neutrino mass mechanisms are designed to have order 1 Yukawas. Okay, and here you see the impact of having mass mechanisms for neutrinos on Higgs vacuum stability. So this was the lambda coupling, the quartic coupling of Higgs, and if it goes negative, then you have a stability problem. And you see in the standard model it just goes negative. We are in metastable regime, but if you add, for example, this is type 1 seesaw diagram. If you have type 1 seesaw with order 1 Yukawa couplings, then the stability problem becomes much worse. So this kind of puts also limits on what kind of models at what order of Yukawa couplings you can put into your theory. Okay, and this is again for low scale seesaw, where again the problem is. And there are solutions also known. I am not going into details. Finally, just last thing. This is a surprising connection that we found. So what is this? This is relating proton decay with neutrino nature. How come it is getting related? Because you know typically gut theories predict proton decay, and they are typically two body decays. Okay, and the general wisdom is that proton decay is a baryon number violating process. Okay, here on the left hand side you have a baryon number 1 object, and there are no baryons on the right hand side. But what people don't realize is it actually is not just baryon number violating process, but it is also a lepton number violating process. And in fact, this thing changes the lepton number by unit 1. This is only possible when the lepton number symmetry is completely broken or at most broken to Z2. Okay. Now, if you have Dirac neutrinos, as I said, Z2, if you break lepton number to Z2 symmetry, you cannot have Dirac neutrinos, which means Dirac neutrinos necessarily require Z3 or higher symmetry. If you do that, then you will find that this process is not allowed, but rather more exotic decays of proton are allowed. And you can see the impact of symmetry. There are always 3 leptons in the final state. Why it is interesting? Because now the proton decay becomes much more complicated and is processed through a very high dimensionality diagram, which means that the intermediate particles involved in this decay process are now accessible to LHC scale. They can be within the TeV, GeV range, and they will simultaneously be also checked by proton decay experiments. Okay, so you can test them at LHC as well as a proton decay experiment. So the line this side is ruled out, and this is the range where you would like to see, and they will have very unique signature. There will always be 3 same sign leptons in the final state. There are other examples I will just skip through, and then there are also cosmological implications for this thing. I will skip because I am out of time. Now, so I discussed few of the important things, and there are some important omissions. I completely didn't talk about Fermi matrices and family symmetries, because this is a talk in itself. Strial neutrinos, coherent elastic neutrino nucleus scattering, etc. I missed. Very important thing which I am regretting to mix is the cosmological imprints of neutrinos, different type of things, changing the order of phase transition, gravitational waves, etc. etc. I hope someday I will get chance to cover those things. Now finally to conclude, there are various interesting possibilities, and one of the most important development in last few years is that people have now started looking at Dirac neutrinos more seriously. And why it is important? Because there are certain characteristics of Dirac neutrinos which lead to new phenomena which are not present for Majorana neutrinos. And as I said that neutrinos are not just, neutrino physics in itself is interesting, but neutrinos potentially connect to other problems in standard model. Some of them I discussed, many of them I skipped, but neutrinos maybe are the for the new physics models that we are looking at. So I will say that in 10 years there are a lot of things going to happen in neutrino physics. All the experiments are running. We hope to see something really exciting. So thank you.
Okay, thank you for a very good talk. We have time for a few questions.
Yeah, one small question. You showed this proton decay. It cannot decay because there is a lepton number violation. But if it decays to 3, that again violates lepton number.
Yes, but now it violates to in 3 units, because for neutrinos to be Dirac particles, you need a subgroup which is Z3 or higher. So if there is no lepton number violation, there is no proton decay. So proton decay will only happen if there is baryon as well as lepton number violation.
Yeah.
Okay. Now what I am saying is that neutrinos can be Dirac particle only if the lepton number is broken to Z3 or higher symmetry. If that is the case, then these 2 body decays are not allowed by the residual. What is allowed are decays which respect this Z3 symmetry. They will always involve 3 leptons in the final state. Hence the complication.
Okay.
All B violating theories are B minus L conserving theories.
No, no.
Okay.
No, no, no. I am saying that proton decay is not just B violating, but it is also L violating. And L violation has important implications.
Because an L appears in the product, but what if it decays into, I don't know, what if it's, I mean, since you're considering an exotic scenario, why not consider an exotic scenario in which the decay products have no lepton number and maybe charge is not conserved?
We know the the particles which are lighter than proton, right? There are only few particles which are lighter than proton, and because proton carries charge, one of them has to carry charge. So there are
So but my point is charge conservation and B conservation are on equal footing right now. We see no experimental evidence for otherwise. If you are going to abandon B conservation, you can just let your proton decay into photons and also abandon charge conservation. Why not?
No. So
I mean, you can't give me a theoretical reason for this because there's no, right?
No. So there are, okay.
In standard model, B minus L is not anomalous. So B minus L is conserved. So if you are going to keep standard model gauge group intact, SU2 cross UL, you will like to have theory in which B minus L is conserved, and that's what is being done.
No, so this combination, if you like to look like that, the combination that is getting violated is B plus L in proton decay. So this is actually a B minus L invariant process. There is no B minus L process.
I agree.
The violation is B plus L. If you want to look in the B plus L, B minus L basis, then this process is associated with B plus L violation, not B minus L. And to answer your question about why I am putting charge conservation at a higher pedestal than the baryon number conservation. The point is, charge conservation has first of all very much more stringent constraints, and second thing is that we also do not really know how to write down a theory where charge conservation, charge violation happens. Okay, because you know the only way to break charge is through spontaneous symmetry breaking. Photon will get mass. There are very severe constraints on mass of photon. In principle, you can have this, but the expectation is that processes which will have electric charge violation will be much more rarer than processes involving lepton number violation or baryon number violation.
Oh, okay. Thank
That's
you.
the idea.
Okay. Any other question?
So, hi, here. As a theorist, basically there have been a lot of neutrino anomalies, like reactor neutrino anomaly or like the sterile neutrino need for that. But we have also seen many tensions recently coming up or other explanations. So what's your take on this? Need of new theories or better look at experiments?
So I tend to take a conservative approach. My thing is that whenever some experiment will run, just because of a statistical fluctuation, from time to time you will get 2 sigma, 3 sigma axis. So one should be, it's not like it's good to, you know, do model building as exercise, but taking 2 sigma axes very seriously is, I am not of in favor of that. But yeah, I mean, as a fun exercise, you can try to see that what if this 2 sigma builds up to 5 sigma, what kind of theory one kind of model. But you should do it with keeping in mind that, you know, you are looking at things which are very much in the realm of statistical factors.
Okay. I think let us thank the speaker. The next talk is an online talk by Professor Vipul Bhuiyan. He will be talking about neutrino physics, the current experimental status. Professor Bhuiyan is from Indian Institute of Technology, Guwahati.
Yes, hi. Hi,
Hello, Professor Bhuiyan. Can you hear us?
yes, it's
Okay.
very unfortunate. Like, I'm still not very well. You can get a sense of it in my voice, I guess. I was down with viral fever for the last 3-4 days and just recovering.
Okay.
So,
Okay, fine. So we are about to start. Should we start now? Okay.
I cannot hear you, Vishal, if you're speaking to me.
Yeah.
Yes, I can hear you, Vishal. Okay, let me share my screen then. Hold on a minute. Okay, do you see my screen? Okay, perfect. All right, so again, my apology for not being there in person, though I wanted to be there. Then, of course, I should be thanking the organizers and also the committees that have decided to invite me to give this main talk on neutrino physics, covering mostly the experimental status of the neutrino physics. And it's a difficult subject because there are a lot of things I had to look at myself to prepare this talk, but I'm glad that I did it. So I'm sure I didn't hear the previous speaker's talks, but I'm sure he has introduced the concept of neutrinos in this model, but I think just to be on the same page, so I need to go through this slide. So again, excuse me if I'm repeating the same thing from the previous talk as well. So in the standard model, we have these neutrinos, the nu e, nu mu, and nu tau, and also the associated antineutrinos. And we know that the neutrinos interact through the weak force, therefore the mediators are the W plus minus and Z naught. And in the standard model, the neutrinos are expected to be a massless particle. And we also know that neutrinos are left in the particle, whereas the antineutrinos are right in the particle. And I think this has implications about the generation of neutrino masses. Now, as an experimentalist, if we are going ahead to detect or look for this particle, we will not be able to do that detection of this particle directly because they do not have an electric charge. So only what we see, only the byproduct of the neutrino interaction with matter. For example, if I'm talking about a new mu charge current interaction, so I should be expecting a muon along this track to be visible in the detector. So that's basically the along this track that I'm expecting if I'm talking about a new mu charge current interaction. So whereas if I'm talking about a new V charge current interaction, so it's going to be an electron track that appears in the detector. And that's because the electron actually goes through a lot of Bremsstrahlung processes and also multiple scattering. Therefore, the electron track is not going to be a straight line just like a muon track. Therefore, it's a little bit more difficult than a muon track. But I think by looking at the topology of this electron track, we should be able to identify that if it is an electron track or not. And of course, the detector has to be sufficiently sensitive to do that. So then if we're talking about the neutral current interaction, then I'll be expecting a production of hadrons. For example, in this diagram here, I have a pi0 production because of the neutral current interaction. And this pi0 decays instantly to 2 photons. And again, you will not be able to detect the pi0 there, but you can reconstruct the pi0 from the 2 photon process if there is a sizable opening of the 2 photons in the detector. So though these particles are very difficult to detect, but then they are quite abundant because they're being produced, a lot in the in the universe. For example, about 100,000 billions of those are passing through our body, which have been produced in the sun, and this is being passing through our body per second, 100,000 billions of them. And just because the interaction cross-section is very small, it's about 10 to the minus 38 centimeters per nucleon at 1 GeV energy. So we'll be able to stop only about the neutrino in our entire lifetime, which is a good thing because otherwise we will be behaving like a neutrino detector. Now there are multiple sources of these neutrinos. For example, if you look at the solar neutrinos, so the sun gives us neutrino in the range of in energy range of 0.1 to 15 MeV, and these are mostly being produced in the fusion reaction inside the stars. And 85% of these neutrinos are actually coming from the PP reaction. Therefore, we should be getting a lot of this new E, the electron type of neutrino from the sun or from the solar neutrinos cases. From the man-made facilities, we have the nuclear reactors. So nuclear reactors produce antineutrinos, electron type of antineutrinos, and these are in the range of MeVs. Whereas the particle accelerators produce neutrinos in the range of 0.5 MeV to almost 18 GeV. Whereas the atmosphere provides us the neutrinos in the energy, in the widest energy range, this almost goes from MeV to almost 200 TeV. Of course, the flux drops very rapidly at high energy there, and that is being seen in this picture. Now, in the last 25 years, we have learned a lot about the neutrinos, and in fact, in the standard model, it's important to highlight that the lepton flavor is strictly conserved in the standard model. Whereas in the last 25 years, we have seen that the neutrinos do oscillate back and forth from one kind to another kind. And in fact, on my personal note, this observed neutrino oscillation itself is a great triumph because, this is a macroscopic manifestation of the quantum effects, the underlying quantum effects. And this neutrino oscillation also indicates that the neutrinos are having some non-zero mass. And it has actually huge impact in particle physics and cosmology. And we have also learned that the mass states are going to be different from the flavor eigenstate for the neutrinos because this is how the mathematical formalism is being decided, being written now. And of course, this was the first signature for the beyond standard model physics because whatever we have seen here in the last 25 years is actually beyond the standard model. Now, we have learned that the neutrinos actually mix, and this is, we have a similar situation in the quark sector. So when I talk about the neutrino mix, I should be able to write down an equation linking the mass eigenstate to the weak eigenstate, or the weak eigenstate to the mass eigenstate by this unitary matrix, which is here is being written as U. And this matrix has to be into a matrix for a 3 by 3 neutrino flavor in this case. And this matrix is called a PMNS matrix. So for the quark sector, we have a similar matrix that is called a CK matrix for the quarks. And these elements of this matrix are pretty much now being measured for both the quark sector as well as the neutrino sector. For the quark sector, in case of the CKM, we see there's a definite pattern emerging where these diagonal elements are actually pretty large and they're also pretty equal, whereas the same is true for the off-diagonal elements as well. But we do not see a definite pattern emerging for the PMNS matrix in case of the neutrino. So this is something to watch out in the long term. Now, this matrix, the unitary matrix, can be parameterized in terms of the measurable quantities, which can be written in the form of the sines and cosines of various angles. And in fact, within this parameterization, you should be able to talk about the neutrino oscillation by 2 delta mass square differences, the 3 angles, and 1 complex phase. And then there are various ways to measure these quantities, the theta 1, 2, theta 2, 3, and theta 1, 3. These are the 3 angles that I mentioned about. And these are pretty much actually known right now, and I think I'm going to talk about it later. The delta CP phase, which is basically appearing in this equation, delta CP, so that is still not known yet. There are some hints, I'm going to talk about that later. Whereas the absolute masses of neutrinos are not known at all at this time, we only have the limits. Whereas the other quantities, these mass square differences, are pretty much measured, and there are different ways of measuring them, which is actually a good thing because then you can cross-check those results from different facilities. I'm going to talk about that later. Okay, now let's look at the status of theta 2, 3 and delta m squared 3, 2. So if you are looking at atmospheric neutrino and experiments, so then you will be sensitive to these 2 parameters, theta 2, 3 and delta m squared 3, 2. And in an experiment where you are looking at atmospheric neutrinos, the signature for that will be a disappearance of an upward going neon-like interaction and subsequent appearance of a tau-like interactions if your detector is sensitive enough for the tau reconstruction. Now, here in this particular table on the right, I'm actually listing the results from the Super K experiment in Japan as well as the IceCube and Andros experiment. Now, at this point, one point I need to highlight here is that these experiments are running at different energies. For example, the Super K is running at around 600 MeV, whereas the IceCube and Andros are looking at neutrinos at a very high energy scale. But the good thing is that these angles, the theta 2, 3 and delta m squared 3, 2, that is being measured from the experimental facilities are actually coming out to be very similar to each other within the statistical uncertainties. So basically, whatever the low energy scale that we are seeing in case of Super K is the physics that is underlying physics at the low energy scale is actually pretty much the same, it looks like, at high energy scale as well. Now, so you can get the same parameters, theta 2, 3, you can measure the same parameters from the oscillator-based neutrino experiment as well. And here I need to highlight the results from T2K NOVA. And in fact, we have the latest result from the NOVA experiment from a lab that gives you the best result on these 2 parameters right now, delta m squared 3, 2 and theta 2, 3. And the precision on delta m squared 3, 2 is around 2.9% already. And for theta 2, 3 is around 6%. Okay, that's the precision that we are doing. And in fact, this is the least known quantity at this time with 6% uncertainty on the theta 2, 3. So if then there's an effort going on to put all this together and do a global fit to understand what is the octant of theta 2, 3. And in fact, it turns out that all these measurements that are being done at both the atmospheric neutrino experiment as well as the oscillator-based neutrino experiment, so this is also pretty much consistent with the maximal mixing. The Super K has a slight difference for the second octant for the theta 2, 3. But I think this is again something, but this is about a 1 sigma, so I think it's not something very alarming at this time, but something that we can keep an eye on in the long term, and hopefully this will be resolved very soon. Okay, on theta 1, 2 and delta m squared 2, 1. So these are being measured at the solar neutrino experiment that is more sensitive to the theta 1, 2 angle, and to some extent also to delta m squared 2, 1 mass splitting. These experiments use the solar neutrino fluxes, therefore they relies on the validity of the solar neutrino, the standard solar model for the neutrino flux measurement, because they have to know what is the flux for the original from the sun that they are saying. And this experimental program for the solar neutrino measurements, so basically they look at the survival probability for the electron type of neutrino in this particular energy range of around 1 MeV to 15 MeV. Now, these are the results. I mean, I'm going to talk about these results from the solar sector, but then there's a complementary results that you can also get from the reactor anti-neutrino data. For example, the CAMLIN is providing us the best complementary results now on these two parameters. And in fact, if you look at these numbers on, this is being shown here, the green is actually coming from the Super K plus SNOW, the combined one, whereas the blue one is coming from the CAMLIN experiment, whereas the theta 1, 2 value agrees between the two different measurements, but the delta m squared to 1, they do not agree that well at this time, so there's a difference of about 1.5 sigma between the reactor data measurement as well as the solar neutrino measurements on the delta m squared to 1 at this time. So, so this is again something we need to worry about. But the good thing is that Juno experiment is going to come up hopefully next year, and I think it's going to resolve many of this issue. And of course, the Hyper K in the long term is going to improve the solar results as well. So hopefully, I believe in the next couple of years, I think this issue is going to be resolved as soon. Okay, on theta 1, 3 and delta m squared 3, 2. So these are mostly being measured, at least for the theta 1, 2, these are mostly being measured at the reactor experiments, where they look at the inverse beta decay reactions with the prompt and delayed photon signal to detect the antineutrinos with the liquid scintillator target. And so basically, they'll be looking at the prompt electron or positron production because of this inverse beta decay process. And then subsequently, there's a production of the neutron that is getting either captured by the proton or the gadolinium if you add gadolinium to the target there. And that is going to give you a delayed photon signal because that is going to excite the gadolinium to a high energy excited state. And this is going to give you a delayed signal for this process. And by looking at these photons that you are getting either the prompt one or the delayed one, you should be able to look at this particular process. Now, these experiments particularly look at electron neutrino survival probability or the antineutrino survival probability. And so if you write down the equation, that equation looks something like this. And of course, you can ignore theta 1, 2 term in this equation at baseline of, let's say, for example, DAE-BRNS, because the baseline is very short there. Now, there's a new result that has come up from the DAE-BRNS experiment on the neutron gadolinium capture because of this particular process. And that gives us the best precision measurement on the theta 1, 3 at this time, which is around 2.8% for the theta 1, 3. And you can also, of course, you can also put limit or you can also measure delta m squared 3, 2 from this experiment. And I think the precision is around 2.3% at this time. So you can do the same calculation or do the same measurement theta 1, 3 from the reactor-based, from the oscillator-based neutrino experiment as well. But the DAE-BRNS seems to be giving us the best result in terms of the precision of the measurement for theta 1, 3, whereas for delta m squared 3, 2, the precision from the oscillator-based neutrino experiments are actually pretty comparable to the DAE-BRNS measurement at this time. Okay, so what are the known unknowns? So of course, the CP is something that we would like to measure in the neutrino sector, and I think that's implication in the way we understand this our universe. And of course, we have seen CP values in the quark sector that many of us are doing at this time. And of course, additional CP values in the electronic sector is going to be quite helpful to understand the matter dominance of the universe. And therefore, this delta CP measurement is going to be critical for in the neutrino sector. So there are some experimental measurements that indicates that, particularly coming from the T2K measurements, that indicates that the delta CP values is going to be large for neutrino sector. It's going to be around 270 degree or minus 90 degree. But again, this requires more data because this is less than 3 sigma. Now, there was an effort to combine the results from the reactor as well as a long baseline neutrino experiment to find out, yeah. Yes. I have 9 minutes. Okay. Okay, I need to go faster then. Okay, so then combining the results from the reactor plus long-based neutrino experiment, the results is far from stable there. So I think again, the future experiments like Dune and hypercase should be able to give us more definite answer on the delta CP. Okay, the mass ordering is not known just because I do not have time. So I'm just going to highlight the important point. So there is a global fit is being performed, and that gives you a slight difference for the normal mass ordering, but that significance is still less than 3 sigma. And of course, we need to wait for the future experiments like Dune, Juno, and Hyper-K to resolve this mass ordering issue. I think this is something that I'll talk about in the next few slides. Okay, the neutrino absolute masses is not known at this time, so we have some cosmological observations that is putting a limit on the sum of the masses of the neutrinos at 0.12 electron volt, but that relies heavily on the underlying cosmological assumptions. Whereas the neutrino double beta decay experiment gives you a limit in the range of 0.04 to 0.16 electron volt. But then again, that depends on the nuclear matrix element calculation. And of course, on the assumption that the neutrinos are Majorana particle. Now, there's another set of experiment that is looking at the endpoint of the beta decay spectrum, because depending on the mass of the neutrino, so your endpoint is going to be located at different locations. So if you have a very highly sophisticated detector to measure this endpoint very precisely, so you can actually calculate the neutrino mass from the endpoint of the beta decay spectrum as well. So right now, the best result is coming from the Catherine experiment is just putting a limit at 0.8 electron volt for the neutrino masses. So there's another experiment, this project 8 is coming up in US, and this is going to put a limit at around 0.04 electron volt, hopefully in the next 5 to 6 years. I think that's something to look around. Okay, on the neutrino-less double beta decay experiments, so there are a whole bunch of experiments are being planned at this time, but I think the ultimate goal for this experiment is to calculate this m beta beta with this particular value of 0.001 electron volt, so that you can rule out or you can actually establish that the neutrinos are Majorana particle, but that is going to require a very large target mass of around 100 to 10,000 tons of detector. So again, I think this is, hopefully I think this is going to happen at some point, but I do not see it happening anytime soon. Okay, now let's look at some of the future experiment on the neutrino. So the Juno is coming up next year. So it's going to be at a baseline of around 53 kilometer, 700 meter on the ground, and it's going to use 20 kiloton of liquid centiliter target detector material, and the signal is going to be read out by the PMTs with that is going to provide us coverage of around 78%. And this detector is going to be sensitive to the reactor type of neutrinos, atmospheric neutrinos, and also the solar neutrinos, in addition to, of course, the supernova and geoneutrinos. So I think that I'm hopeful that there will be a lot of exciting physics going to come up from Juno experiment. In fact, if you look at the precision measurement for the oscillation parameters, particularly the delta m square 32, the 2.1 and also 1.2, these quantities will be measured to less than 0.5% in about 6 years of time by the Juno experiment. And if they only look at the reactor neutrinos, so they should be able to resolve this mass ordering issue at the 3 sigma level in about 6 years of time. So this is basically the sensitivity of the mass ordering as a function of time that Juno is going to be doing. Okay, so then there's another experiment that is being planned under construction is the Hyper-K experiment at ZPARC. This is going to be having a baseline of 295 kilometer, and they're going to use a 1.3 megawatt of beam. The detector is going to be 2.5 degree of axis, and the beam is going to peak at 0.6 CP energy. And they're mostly going to look at the force oscillation maximum to look at this oscillation phenomena. And this is being done just to ensure that they have large number of statistics coming from this Hyper-K detector. So in terms of the absolute masses of this detector, so compared to the superconductor experiment that is running right now, so it's going to be, Hyper-K is going to be about 8 times larger than the Super-K detector. So they're going to use the same detector system as the T2K at this time. Of course, the ND280 off-axis detector is going to be refurbished, and they're going to put additional detector material there. because they need to improve their flux measurement as well as improve their neutrino interaction model as well for the cross-section calculation. So hyperjets should be able to do the CP as well. In fact, because they're going to look at the CP through the measurement of the probability of nu mu to nu e oscillation as well as the probability of nu mu bar to nu e oscillation. And in fact, with 10 years of running, so they should be able to collect about 1,000 nu e and nu e bar signal events, and therefore they should be able to in about 10 years of time, so they should be able to remove or exclude at least 61% of the delta CP values at around 5 sigma level. So that is what they're aiming at this time. On the mass ordering, it's not going to be very easy unless and until the Hyper-K experiment is going to combine the atmospheric neutrino observations as well, provided the mass ordering is not known by the time the Hyper-K starts collecting data. So they will require to combine both the accelerator data as well as the atmospheric neutrino data to say something definite about the mass ordering in about 10 years of time from now. Now, DUNE is a experiment that is being planned in US. In fact, this is under construction at this time. So this experiment is going to use 1.2 megawatt of beam from day one, and that's going to be upgradable to 2.4 megawatt. And as a fall detector, it's just going to be a 70 kiloton liquid argon detector, and this is going to be at around 1.5 kilometer deep underground. And there's a new detector complex is going to come up at around 7. This is construction at this time, so that's the excavation of the far detector site is happening right now. It's going to require. Hi, Vishal, can you hear me still? Vishal, can you hear me? Can you hear me? I think I lost connection in between, I guess. Okay. Okay. All right. So for the DUNE fall detector, so there is going to be a in the phase one, so there will be a horizontal drift module, and also there's a vertical drift module that's going to be put in place. For the fall detector side, there are two modules are still, the technology for those two modules is still undecided. And of course, if you have ideas, we can talk about that as well. Okay, I can skip that. So this beam upgrade process is happening right now for the LBNA beam. And this is something I need to highlight here, that India is playing a big role in making this happen, the PIP2 beam facility. So that is going to provide us the beam for the DUNE experiment, and it's going to give us the beam in the energy range of 0 to 8 ZeV. And we are going to use this broad energy beam for this experiment. That's going to help us to look at both the neutrino first and second oscillation maximum. So this is basically, in this picture, you can see the near detector compass that is getting constructed at this time. So in the phase one of the near detector complex, we're going to have a liquid argon TPC, which is shown here in the black box there, followed by a small temporary muon spectrometer, which is going to be upgradable to the ND-GAR detector in phase two. And there's a system of on-axis neutrino detection, which is basically a SAN detector, which is going to remain on axis to monitor the beam throughout the lifetime of this experiment. And that is something that Indian institutions are participating at this time on DUNE. Okay, let me skip that because there is no time to talk about that. So in terms of the physics, the CP violation sensitivity, because this is something that we would like to do in DUNE, and in fact, we should be able to do the 5 sigma discovery for the CP violation for CP values. And the resolution that we'll be expecting on delta CP is in the range of 7 to 16 degree. And to do that, we only require this actual input only for the solar parameters. Okay, but because the rest of the things we can measure in the same experimental facility. The mass hierarchy we should be able to do in about 1 to 2 years of time after running this experiment with about 1.2 megawatt of beam. And in fact, there is some recent paper that has come up that has indicated that even with a low exposure like 66 kiloton megawatt years, we should be able to resolve the CP violation, the mass hierarchy issue in the Dune experiment. Now, I need to highlight about this complementary nature of the Dune and Hyper-K experiment because many times these are being categorized as a competing experiment. But then if you look at the delta CP coverage as a function of the sine square theta 2, 3 on the x-axis here, none of these experiments will be able to resolve this delta CP value at around 3 sigma for more than 75% of the time. So, but if you combine the two results from these two experiments, you should be able to go all the way to 85%. So therefore, I think it's important to remain engaged with both this experiment because this is something that has to be resolved, and then the CP issue has to be resolved in the very short term. Okay, so that's basically my last slide. So what we are entering is a very exciting era in neutrino physics. And in fact, in the next 10 years, my assessment says that we should be able to do the mass ordering and also to measure the delta CP values. And we should be able to measure the oscillation parameters very precisely to less than 1% level for most of the parameters in the neutrino oscillation sector. And we should be able to test the validity of the three-neutrino mixing model without any ambiguity. At the same time, we'll continue to look for the proton decay and also the neutrinos from the astrophysical sources such as supernova. In about 20 years from now, hopefully, the absolute neutrino masses may be measured through the cosmology, the beta decays, also neutrino beta decays. And whether neutrinos are Majorana particle or Dirac particle, I believe we have to wait about 30 years time from now to understand the nature of the neutrinos. So certainly an exciting time ahead. And before I end my talk, I think let me say that it's my apology that I didn't say anything about the INO experiment in India, and that is mostly because there's a talk that is coming up on INO after this. So thank you.
Thank you, Professor Bipul. Now we can take a couple of questions.
Can you? I guess you can hear me, right? Or so I was interested to in the penultimate slide you talked about the complementarity between Dune and Hyper-K, but I wanted to learn about the competition part, and particularly given the timeline of Hyper-K and Dune, I wanted to know that about the delta CP and another thing, like how's that going to come out, like of the two from the competition side.
Can you please just sum up a crisp question to him?
I actually didn't hear it, so can someone repeat near the mic, please?
Okay. Yeah. Gagan. Okay. So the question is Dune versus Hyper-K. What is your comment?
Competition.
Yeah, what is it?
About delta CP. The CP.
Regarding delta CP.
Yes. What is the question? Oh, the competition. Well, Well, Hyper-K is going to collect data in 2027 roughly, whereas Dune is not going to start before 2031 with the beam. So I believe they are going to be at the same time. I believe that's my understanding at this time in terms of the physics output that they're going to have. Hyper-K maybe is slightly ahead of the Dune to start with.
Okay. Okay. Thank you, Professor Butpul. We come to
Thank
the
you.
closing. All right. So let us thank the speaker. We now go on to the last talk of this session by Professor Indumati, a very accomplished physicist, and she's from Math Science. She's going to talk about India-based underground experimental status.
Oh my God, what was that? Okay. Can you hear me? Okay. It's been a long day. I'll try to finish.
Yes,
as
ma'am.
fast as
Your
I
time
can.
starts now.
Yeah. So I'll start by thanking the organizers for inviting me to give this talk. And I'll also start by apologizing to the people who heard this talk a few weeks ago in Bangalore. But on the time scale of INO, I think 3 weeks is a short time, so I may be excused. So I have been given two introductions, one to the theory and one to the experimental side of neutrino physics. But just to put things in context, I will actually highlight a few things. So what is INO? INO is a proposed and actually funded in principle project, which is a data science project of jointly funded by the Department of Science and Technology and Department of Atomic Energy, and it has two goals. Something fell? Okay. One was to construct an underground lab. All neutrino experiments are underground for getting away from the cosmic ray background. Underground lab to house a neutrino detector, and the other part is an R&D center for detector development, which has actually started already and has been functioning for the last dozen years or so in Madurai in South India. I will say something about that towards the end. The main detector to be hosted is the magnetized ion calorimeter detector, which we call ICAL. That is the actual neutrino detector to be put in the underground lab, both of which are yet to be constructed and have been lying in that status for a long time. So that is my one-line summary of this whole thing. But let me say something about what is the physics that we will be able to study at ICAL. I also want to highlight that the INO graduate training program has been extremely successful. About 40 PhD students, most of whom have already got their degrees, have come out of this place, have been trained both in experiments, simulations, and in physics. So a completely indigenous project. And so it was. So what is it going to study? I mean, the lack of accelerators in India means that you must look for a naturally occurring source of neutrinos, and one naturally occurring sources are the atmospheric neutrinos, which are produced after the primary cosmic rays decay to produce muons, which decay to produce nu mu and nu e in the 2:1 ratio through these processes. I hope you can see them. And so any deviation from this ratio, especially as a function of direction, which is a function of the path length that the neutrinos travel, will be a signature of neutrino oscillations, which we already know exist. So what happens when these neutrinos reach the detector? They will interact with the material of the detector through a charge current interaction and produce, the nu mu will produce mu minus, the nu mu bar will produce mu plus, plus some hadronic debris, and the magnetization or the magnetized part of the ICAL, the magnetic field will actually bend these two in different directions, and therefore you can separate out event by event mu minus from mu plus, which means you can separate out event by event mu induced versus mu bar induced events. And the reason we need to do that is because that is precisely what is required to determine the neutrino mass hierarchy. So how will we do that? Before I say that, a few words about the proposed experiment. 17 kilotons is a very favorite number. Each module of Dune is 17 kilotons. Each module of INO is also 17 kilotons, 51 kilotons in all, with 151 layers of iron, 56 millimeters in thickness, and in the gaps between them, 150 RPCs, which are the active detector elements, will be placed. So when a charged particle goes through it, there is a discharge, and each of these, as the muon, for example, passes through the detector, you will find a signal, and by joining the dots, which curve in the magnetic field, you will be able to actually determine the momentum, the direction, and the charge of the muon that pass through. So the main thing about atmospheric neutrinos is the huge range in both energy and angle that is affordable, and that is actually a very, very nice input that will go into the calculation. We will see it later. So just to complete the details on the detector, the magnetic field will be maximum 1.5 Tesla in the central region, and I mean, of course, vanish towards the end. The number of RPC units of 2 meter by 2 meter that are required is about 30,000, with associated almost 4 million channels of electronics. So even if you have a large collaboration, this is not something that you can build in a lab. So huge industry interface is required, and a lot of that work has already been done for the small detector that has been running for almost 5 years in Madurai, which I will show towards the end. So what can we learn from ICAL? So this talk now, this part of the talk is just the physics part. So we'll talk about oscillation probabilities, theoretical fluxes, theoretical numbers, and after understanding the physics, I will actually go over to the more detailed simulations and show the physics potential, and I will end by saying what is the actual construction status. So what we've already seen this before, so we don't know the absolute zero of masses. We also don't know whether M1 squared is the most massive or the, M3 squared is the most massive or the lightest of the neutrino masses, and therefore this is called the mass ordering problem. And if the question mark is sufficiently close to zero, the mass ordering problem is also the mass hierarchy problem, because this number is becoming smaller and smaller. So the determination of the 2-3 mass ordering will also determine the neutrino mass hierarchy, apart from which we know that the mixing angles are large, and this question of the octant has already been beaten to death. Whether theta 2-3 is greater than 45 or less than 45 is called the octant problem. And because the across generation mixing angle is large, CP violation is measurable. It doesn't really matter to us except in an indirect fashion. I will talk about that also towards the end. And delta CP also is different for the matter and antimatter interactions, and that will mix up with the matter dependent signal, and that is the only reason that I'm even talking about it here. And this is the background context in which INO is being built, and I forgot to mention, which was already mentioned in both the talks, that we only know the magnitude but not the sign of the 2-3 mass squared mixing. So here is INO, something wrong, okay. So here are the probabilities in matter for the dominant mechanism, which are the mu events, the mu atmospheric neutrinos, because ICAL is tuned to actually study or optimized to measure the properties of the muons which pass through it. So this is the P mu, and you can see the dip and the rise. And if you look at it in the two-dimensional plot of, this is with respect to L over E, L being the path length and E the energy. But if you unwrap it into a 2D thing, you can see the structures over here, which are the matter effects. And these are what will actually be, this is for normal ordering. This will be, these structures will be seen in the antineutrino sector for the inverted ordering. And by actually looking at them separately, you will actually make a measurement of the mass ordering. So here are some details. This is the relevant quantity. These are some mixing angles in matter. Doesn't matter what it is. But this delta M squared and A has plus sign for neutrinos, minus sign for antineutrinos. Sign of delta 1,3 is not known. So depending on whether delta is plus or minus, the cos 2 theta 1,3 can equal this ratio or not. And therefore, there's an enhancement, which is the MSW enhancement of this angle in matter, either in the neutrino or in the antineutrino sector, and that is really the crucial input that goes into determining this mass hierarchy. The same expression, if you look at it in a little different way, this is an approximation. These are just to make it easier to understand the problem. Is the octant of theta 2,3 is a subdominant problem. It's already hard to find the matter effect, but the theta 2,3 appears here. You can see here in orange and here in red. The one in orange cannot distinguish the octant because it's proportional to twice theta 2,3, whereas these two can determine the octant, but they are suppressed because of this theta 1,3 factor, which is small. So it's a very challenging measurement to make. I don't want to say anything more here. I don't want to say this. Okay. Okay. So now this is really the background of, what is the kind of physics inputs that we saw. Now I'm going to actually show you some results with some detailed simulation studies of the same thing with some more details. So we have done a detailed JAN4 based, we have done many JAN4 based simulation studies. This is a very typical, very optimistic event with a very long muon track. Some events scattered, some hits scattered near the vertex, which is the hadron shower. So the hadron shower is very poorly determined. We will not be able to actually even determine how many objects there are in that shower, how many hadrons there are in the shower. But we do have some minimal or coarse energy and direction reconstruction from these hadron shower elements. So we use a Kalman filter algorithm. You can nicely bend track to reconstruct both the sign of the charge and the momentum of the muons. And of course, as the muons are produced closer to the edge of the detector and they start going out of the detector, you will find that the reconstruction quality is poorer, and that shows up over here where the x-axis shows the simulations of the true momentum versus the sigma by p obtained for 4 different quadrants in the azimuthal angle. See, everyone thinks of iCal being a nice rectangular dabba. It's a very simple thing to simulate in GANT. But because of that, unlike, for example, LHC, there is no cylindrical symmetry, no spherical symmetry, there is no symmetry at all. And the presence of the magnetic field breaks all your X, Y, Z symmetries. So actually, in fact, if you look at it carefully, there are different reconstructions in different azimuthal angles, in different cos thetas, which are all these colored lines, and in different energies. So actually, the analysis does become complicated because of that. But the event rate is small, so you can spend your time very carefully reconstructing every event, so it's not like LHC. And you can see that the best response is in the region here, which is the region where you expect the matter effects to be large and the MSW resonance to occur. Okay, so here also I have shown the reconstruction efficiency about 80 to 85%. The charge, you can't read these axes, just believe what I'm saying, sorry. The charge ID efficiency beyond about 2 to 3 GeV is greater than 98%. So you can tell the correct sign of the muon charge to better than 98%. And this is, of course, about 100% by square root T being the energy resolution of hadrons. So this is what you have. So the first result that I'm showing you is a precision measurement of sine squared theta 2,3 versus the modulus of delta M32 squared. And sorry for this misalignment, but I have tried to make it such that the y-axes are actually, I've scaled the size of the figure so that you can compare the potatoes identically on both sides. So the red potato here is the iCal reach compared to all the other experiments, but please note the bottom line that iCal is yet to be built. So then we come to the mass ordering, which is what we call the central goal of iCal. There are 2 different curves here. Look at the red curve. So this is as a function of runtime. You can get about 3 sigma in about 10 years worth of running, which actually improves by some bits and pieces if you add some more details. But this is roughly it. The main, point I want to emphasize is that this result is independent of the CP phase. So you saw all those oscillating curves for the dune, T2HK, etc., Minos, Nova. That is not the case. It's a completely accidental discovery that the energy range and the length in which the MSW resonance occurs in atmospheric neutrinos is such that it is completely independent of the CP phase at that point. And if you want to look at CP phase in atmospheric neutrinos, you must look at the low energy region. So it just happens that way. It's a very nice result, and therefore this result is a very robust and strong result. So I want to just add a few words. I've added this slide forever. I think I've shown it for at least 10 years, just keeping on updating this. That matter effect or the mass hierarchy is not only the centerpiece of iCal physics, but because it is it addresses such an important and central question about whether neutrinos neutrinos are Dirac or Majorana. This is the lightest mass eigenstate versus the neutronal double beta mass m double beta over here on the axis. That it is something that is being probed or will be probed not only but by INO but by MINOS, T2K, NOVA, Pingu, IceCube, Juno, Dune, etc. So each is an amazing experiment, but just the sheer number of experiments listed here tells you the importance that the community is giving to that problem. And as I said already, that most other experiments have to disentangle the effects of CP from their matter effect, but this we can use by actually considering it as a synergy. For example, while the green NOVA has practically no sense. Okay, done. The spelling is checked. Sorry. Where was I? Yeah. So NOVA had practically no sensitivity in this half of the delta CP plane, but by including other experiments, this goes up, and then you get a good or a much better discrimination of the hierarchy. And this is for the same thing happens for the value of delta CP itself. So there are many synergies. I have only shown two over here that will improve the results by combining judiciously different experiments, keeping in mind that their statistics and systematics are all different. So there are other physics that you can do with ICAL. For example, we do have neutrinos of electron flavor type, though they are 1:2 in number, and ICAL is not actually optimized to see the electrons which are coming from the charge current interactions, but it has been done. It has been said of neutrino physics that every neutrino event is precious because they are low counting experiments, so you don't want to give them away and abandon them just like that. So you can see that there is a certain sensitivity to the theta 2-3 angle, not to the delta m squared if you include some electron neutrinos through some very tortuous method, which I don't have time to talk about, which is called trackless, and that you can see that some sensitivity can be added in that channel. The other channel where you can include sensitivity is by looking for tau neutrinos, which are also produced, because if you look at the neutrinos coming from the atmosphere on the other side of you, they undergo oscillations as they come through the Earth, and in fact you'll see that IceCube has already shown that there is like 1:1:1 ratio of the neutrino flavors from the other side. So there's a huge number of tau neutrinos. Unfortunately, the flux falls like e to the power of 2.7, 1 by e to the power of 2.7, and therefore, the threshold for charge current tau production is 3.5 GeV. So the number of tau neutrinos is very small. It's a hard experiment to do. ICAL will have a detection efficiency of about 4 plus sigma, just for, by the way, all these results are for 10 years running, okay? About little better than 4 sigma for actually showing that the taus exist and they have been produced in the detector. And if you include the tau along with the standard muon analysis, then you actually improve the discrimination of the octant, especially if the true octant is in the lower octant. So this is an example. These are at the edge of the allowed 3 sigma allowed region, but you can see that something which was not discriminated at 2 sigma now becomes discriminated at 2 sigma. The wrong octant will vanish. It will not be allowed if you include the tau along with this thing. So there are many other physics details, many of which I apologize for this, since my talk is practically after all the posters and panel sessions were over. Normally one would list out all the talks so that you could go and listen to them, but I think I could not do that. So there were many talks on sterile neutrinos. It will be hard to do in ICAL. You can probe non-standard neutrino interactions. You can probe invisible neutrino decay, oscillation plus decay, signatures for Lorentz invariance violation, long-range leptonic forces, etc. And this is something I forgot to say when I showed you that graph. Maybe I have the time for it. Here, you can see that this black dip, which is corresponding to this L by E about 2.7, given the current oscillation parameters, is what they call the oscillation valley. And these regions actually come, especially when theta is greater than about 33 degrees, or the length is greater than 7,000 kilometers, you're actually going to probe the Earth's core. And so you can do Earth tomography, and in that region is actually, you can see over here, and there is a lot of matter effect. And so if you change the core density, the core dimension, or do other things, put dark matter in the core, you're going to actually see signatures of that in your oscillation events shape, and that can actually help you probe and do what is called neutrino, sorry, where did that go, neutrino tomography, and that is, as I said, very special because you have neutrinos from the atmosphere coming over all 4 pi. What happened? Okay, so there is some non-oscillation, non-neutrino physics also which has been done. Probing solar dark matter, some limits have been set. Probing earth dark matter in the core, some limits have been set. Wherever you see ICAL is the result. Looking for magnetic monopoles, very nice, slowly moving magnetic monopoles. So they take time to go from one layer to the next. So you know that they are not muons, and leaving hits in the detector. So you can, there's a region here, the nice green region, which you can actually see 10 power 10 to 10 power 16 in mass, and beta from about 0.1 or less, you can see, and the bounds are little better or marginally better than the macro. So there are lots of exciting possibilities, and that is really the bottom line. So there's something called ICAL++. I will talk about it a little later because this is an idea of something that was inspired by the Kolar events. I will talk about it in the context of something that is happening in the construction side, something about atmospheric nu E and delta Cp, which I am going to skip. So I am going to now come to INO, R&D, and current status. Current status I have already said. So that is the current status. So what is the current status? I have no answer. So I will go on to the cosmic veto. I'm serious, I don't have an answer. We are waiting for clearances, so we are still waiting. So I will rather go to the I will rather go to the to what is actually happening, what is the R&D that has happened so far, and I like to show this progression of slides because the INO collaboration learned to make RPCs about, yeah, thank you, 10 years, no, 15 years, I don't want to say how many years ago, and mastered the art from, in fact, I used to have a picture where they started with 30 centimeter by 30 centimeter RPCs going to 1 meter by 1 meter, 1 meter by 2 meters, and then the 2 meter by 2 meter, a huge thing. You can see it needs a crane to be lifted. The glass makes it so heavy. So characterizing it in the stack, learning all about it, and finally, what has recently happened is actually the automation of the RPC manufacture by industry in Sriperumbudur. They have actually set up a plant, and our people have gone and taught them how to do this, and they have actually automated the whole thing, and they are churning out RPCs, which of course needs validation and testing. So that's the status. Similarly, we started out with the electronics. You can see in the earlier, and the whole progression again, ending up with all the various parts, front end, back end, data acquisition, etc. Now moving to FPGA as well. So everything is in place now. All the bits are in place. And almost 5 years ago, the mini ICAL 85-ton prototype was set up in Madurai. Madurai is supposed to be the R&D center. It was set up as the R&D center, although we are still working out of rented premises, so the area there is limited. So now you can see what I'm talking about. The golden objects are the copper coils, which are hollow for cooling water. So these copper coils go all the way down. That's why there's a gap at the bottom, so that they magnetize these blue or gray, I don't know what color, iron plates, which are 11 in number, and there are about 20 RPCs inside, excuse me, and so these RPCs are very good in the, and function very well in the presence of these magnetic fields, and well, various gas pipes, everything that you can see, and this has been characterized for a long time. A lot of the students from nearby colleges had fun actually putting the stuff together. I saw a huge amount of enthusiasm from local students that they could actually do something hands-on, and I think our students also enjoyed themselves. Here are a very bad set of practically the first hits. You can kind of, if you look very carefully, you can see the bending of these tracks in the detector. There's the XZ and YZ planes, and as I have already said, the huge participation, very enthusiastic. So what have we learned from this? A lot of time was taken to actually understand because the magnetic field itself. So a lot of detailed study of the actual magnetic field and the comparison with simulations is also ongoing right now. It's also important, it was an important way to validate the codes. That's why this prototype was built, because in two ways, not only the Giant-4 simulation, because you have to understand the cosmic ray background as well as the atmospheric neutrino flux, but also the Kalman filter algorithm that was used for the muon track identification was used for the cosmic ray muon. There are no neutrinos here. There are very, very few neutrinos which will actually be captured in this 85-ton machine. So you will find lots and lots of, millions and millions of cosmic rays, 1 per square centimeter per second on the surface of the Earth. So this is the simulation that was done with the Corsica cosmic ray flux, and that is the red line that you can see, and the blue line is the actual data that was obtained from this mini ICAL, and you can see that the negative momentum only means the opposite charge. I have a feeling that this is the positive muon and that is the negative muon, but I have forgotten. So up to 3 GeV, you can see that not only the atmospheric neutrino flux measurements have been validated, but the Kalman filter code that reconstructs the muons both in magnitude and momentum, both in magnitude and in charge sign as well. So this is what I wanted to talk about in the ICAL++, a cosmic muon veto detector. Since we haven't got clearances for an underground lab, we said, what happens if we try to find a shallower depth and then try to have a veto on the top to veto out the cosmic ray muons, because they are only coming from the top. So the idea is to have actually a cover of about 3 to 4 layers of scintillator on the left side, right side, back, and the top, leaving one side free because you need to go and maintain the RPCs and do some maintenance and some stuff like that. So this is what the whole schematic was. And here in the next slide, I'll show you the current status of the detector. That here is the framework for putting all these scintillator panels. These are the actual scintillators themselves. They are 5 meters long, really long, because they have to cover the entire top and then the sides. So these are just ready to be put in place, and some fantastic work has been done. In fact, it has been running all through the pandemic and taking data. So now it's just been switched off in order to put these cosmic muon vetoes. And if we have a proof of principle that we can reduce the cosmic muon flux by about 99.99%, and if we can actually show it for this mini ICAL detector, then it will give us hope that even if we don't get as low a depth as we wanted for our experiment, we should be able to use a cosmic veto to actually do the. So here is my this thing. I think there are many current and future proposed mega science experiments, not just ICAL. Some like INO are completely indigenous. These experiments are set to probe some of the most important frontiers of physics, astrophysics, and cosmology. And I think we have to repeat again and again what possible outcomes are there, because today there is a question that seems to trouble the bureaucrats the most. What do you get by funding such projects? So I think the invaluable human resource training and development that I have personally seen, not just the students, but also the technical staff, the kind of training, because a number of engineers of different types who are part of the project, a number of people working on simulations on various aspects of the detector, midterm outcomes, doing state-of-the-art R&D detector design, long-term outcomes, which can be all kinds of applications of such fundamental science research. All these are very important to highlight. So I'll just end by saying we have a proof of principle of various components of ICAL. The mini ICAL has some preliminary results which look very promising. Already a great deal of interaction with local industry, which is helping us to construct all these parts. There's a plan to build a scaled up 1/20th scale mod of one of the modules, 800-ton engineering prototype in Kolkata. Well, I believe we have proven the value of a greatly successful INO graduate program and highlighted therefore the importance of a homegrown experiment. This is my one-line summary of status. In spite of these delays, we believe that the physics reach of ICAL will be complementary to current and future detectors, and that INO will galvanize science across the country by offering opportunities to students and industry to work in a cutting-edge research atmosphere. So thanks to all collaborators, especially students, and this is my one-page summary which I was asked to give, so here it is. Thank you very much.
Thank you very much for a very exciting talk. Questions?
Yeah.
So, yeah, nice talk. And so in the detectors, when you are measuring the tracks, how are you sure that the tracks are from the atmospheric neutrinos and they're not from any geoneutrinos coming, in the backward direction?
Are you talking about the main ICAL or the mini ICAL?
I mean, any ICAL.
No, the answers are different. Okay, let me say, suppose you have, in the mini ICAL, they're 100% atmospheric muons, because you can calculate in the big, that humongous 51 kiloton ICAL, which is the size of a 5-story building, you're going to get 3 muon neutrino events a day, okay? So that's it. So whatever you get from an 85-ton prototype is going to be atmospheric muons, and therefore you just collect all of them. That's it. That is the short answer.
Okay.
For the big ICAL, the question is very valid. How do you know that these are not these are neutrinos induced muons which are produced and not just cosmic muons coming from outside? If you go 1 kilometer underground, you still have about 3,000 cosmic muons per hour background flux. So what you have to do is you have to remove the top 2 layers. So you have I didn't tell you that the RPCs have a better than 95% efficiency. So if you take 2 layers, so 0.05 squared is your rejection rate. And so if you say that I insist that there should be no vertex in the top 2 layers and then take all the events below that, then you can be reasonably certain that you have cut out the cosmic ray muons and you have only got events because the neutrinos come in, don't leave a track. When they interact, they will leave a track so that the vertex will be somewhere inside, right? It will start, and therefore the timing is very important, and these are fast nanosecond detectors. So since these are relativistic particles traveling at 30 centimeters per nanosecond, and they are like roughly 10 centimeters between 2 layers, if you cross at least 3 to 4 layers, you know that the direction is kosher because your timing gives you that information, and then you know that it's an atmospheric.
Right. Thank you.
Any other question?
This about this muon veto, as you are also saying that you can use these 2 layers for muon veto, and we already have I think 16 layers in the full ICAL. So suppose you use some layers, let's say 3 or 4 or 5 layers for vetoing, then you can you use it at ground?
So the problem here is the numbers. If you are on the surface, then you have one cosmic ray muon per centimeter squared per steradian per second. If you look at the size of the detector, that will translate to roughly 10 to the 8 to 10 to the 9 cosmic muons per year. No, sorry.
Yeah, that I understand. What I'm
So
saying
it's a matter of
is
statistics.
you can go on increasing some number, this RPC
no,
layer.
what will happen is that you will probably fry your electronics because there will be just too many. That is the problem. See, there's also a noise rate. I mean, it's not, there are randoms, there are singles. So the noise rate is about 100 hertz. So already you are dealing with that. So they are singles. So you can actually deal with them. You won't have a track of at least, going through 3 layers within some time window or something like that. But yes, I mean, if you actually, I have done this simulation. I tried up to 20 layers. Even if you cut out the top 20 layers, I mean, you will lose a lot of your fiducial volume. I mean, actually, Super K does that, right? Super K has a 50 kiloton detector, but their inner fiducial volume is only 25 kiloton. They lose 50% of their detector in this. But so the cosmic veto is, in case you are not able to go to very deep depths, then of course you will put the cosmic veto. If you are able to go to 1 kilometer depth, then you will save that money. You don't want a cosmic muon veto. So that is the idea. So when we say shallow, we mean even 100 meters may be enough.
Any more questions?
So you showed the momentum spectrum. How was it measured? I mean, those muons would be going through the detector.
From the curvature of the tracks, no? So this is the first prototype where we actually have the magnetic field in place. So we have 900 ampere current, so we have a magnetic field up to about 1.5 Tesla in the central region. So I didn't tell you the details actually, sorry, I'll show you the thing again. Only the central region, so you can see that there are, these are the 2 copper coils, and the region inside is where they have taken the data from for now. Of course, there's also a magnetic field outside and RPCs outside, but the data has come from the inner region. So from the bending of the tracks, here you can see that.
So here bending of the
sorry.
So here bending of the track is not going to follow the circular geometry as there is a continuous energy loss. So if the muon is passing through, then just because the track is bending, I don't know how the momentum can be.
You can see why we have a result only till 3 GeV, right? Here. I mean, it's only the low energy muons which will bend enough to actually reconstruct. So the thing is that these cosmic ray you get million events a day, right? But you're only pulling out those events for which you can actually reconstruct the track. As you point out, for very energetic tracks, you'll practically get a straight line in the detector, and you're not going to reconstruct that. So, but even if your efficiency is 1%, you have a million events a day, right? So that is why you're actually going to have a result from the cosmic ray muon flux. This is a 2 meter by 2 meter, right? So you already have 10 power 7 events. It's a large number. So they have picked out those events, sorry, I'm blocking it. They have picked out those events for which the momentum is small so that the curvature is actually visible and the Kalman filter actually works.
Okay, we can have one last question.
Who is asking?
Okay.
No one is asking. It is
I have
very late. I really appreciate you staying so long and listening to this.
I have a non-neutrino question.
Huh.
You said that there are 40 students who have already got their PhDs on this. In how many years?
When did we start the who is here? Amol, when did we start the graduate program? 13 batches.
So I was just wondering, I was trying to compare, you know, with LHC, you know, we have had something like 100 students over 22 years.
Oh, really? Is this a good number or a bad number?
I think this is a very good number.
Oh, fantastic. Thank you. No, but I'm serious. I'm so proud of the students. I've learned so much from them because they learn all kinds of things and they're experts. You know?
I think
I feel so sorry that this project is struggling so much, you know.
So you are still waiting for the clearances? Okay. Okay, so let us thank the speaker and we close the session for today.